Okay, so this is the PANcast for Spring 2018 Physics 102 first midterm second question. We are asked to consider a spherical thick shell, so the inner radiuses are 1 and the outer radiuses are 0. This is a non-conducting sphere, which means wherever I put my charges, they just stay there, they don't move. So a total charge Q is distributed uniformly in this object, which has an inner radius of R1 and outer radius R0. Now, the first part asks us to find the volume charge density ρ. What will that be? It will be the total charge of this object divided by the volume. What's the volume of this object? The volume of this object is volume of the outer sphere, which is 4 pi over 3 R0 cube, minus volume of the inner sphere. So this is all going to be Q over 4 pi over 3 R0 cube minus R1 cube. Good. Now I need to find the electric field as a function of R for three different regions: inside the halo, inside my spherical shell, within my spherical shell, and outside my spherical shell. In all cases, because the problem has spherical symmetry, it's best if I use Gauss's law. And whenever I have spherical symmetry, it doesn't matter what's the radius of my Gauss surface. On all points of my sphere, E and dA are going to be parallel. So this flux integral will always be E magnitude times the surface area of the sphere, which is going to be 4 pi r squared, where r is the radius of my Gauss surface. So then we can actually look at three different situations. First, let's look at inside the halo of my spherical shell. R is less than R1. So here, let me try to redraw this figure. So I'm taking a cross section of it. This is going to be my inner radius, going to be my outer radius, and my Gauss surface radius will be smaller than R1. Then, what's the charge inside the Gauss surface? Inside the Gauss surface is totally empty. Q in is 0. What does that mean? It means that electric field is 0 for R less than R1. Now I can consider the region between the inner radius and the outer radius of my shell. So again, if I take a cross section, that's going to be R1, that's going to be R0, and now my Gauss surface will have radius R. Left hand side of the Gauss law I can easily write, I've done it once, 4 pi r squared, that's going to be Q in over epsilon 0. But what's Q in now? Where are the charges which are in the Gauss surface? They are between the Gauss surface and the inner radius. So Q in this region must be rho times the volume of that spherical shell, which has 4 pi over 3 r cubed as the outer sphere and 4 pi over 3 r1 cubed as the inner sphere. Rho I have already calculated in part A, so 4 pi over 3 is cancelled, which gives me Q r cubed minus r1 cubed divided by r0 cubed. Right? So what's the electric field magnitude? That's what was asked. It's going to be Q over 4 pi epsilon 0 r squared. But now I have this factor which is r cube minus r1 cube divided by r0 cube. And that is the expression for the electric field when I am between the two radii. In the final case, when all of this object is within my Gauss surface, so R is larger than R0, then Q in is Q, all the charges in this surface. So left hand side of my Gauss law is the same, 4 pi r squared. Right hand side is Q over epsilon 0. This is exactly the same as the field of a point charge, 4 pi r squared. Let's write it in the usual order, 4 pi epsilon 0 r squared for r larger than r squared. We have actually calculated the magnitude of the electric field as a function of r for all three regions. How about the potential difference between the inner and outer radii? Well, if I know the electric field, which I've just calculated, I know how to calculate the potential difference, which is going to be V at R0, right? No, it's actually asking the reverse, V at R1 minus V at R0. It's going to be integral E dot dl from my initial point to my final point. Okay. Let me disregard science for a moment. Okay, let's forget about what that dot product means, that means. But here is the thing, what's the expression and what's dl here? dl in this case, dl magnitude is dr. I'm actually going from the inner radius to outer radius on a radial line. So what's the inner radius value? R1. What's the inner outer radius value? R0. What's the electric field expression between these two radii? It's what we have actually calculated there. Q over 4 pi epsilon r squared. But now I have two terms, r cube minus r cube divided by r0 cube dr. So this is actually not a very hard integral to calculate. Q over 4 pi epsilon 0. These are just constants. I took them outside the integral, and inside the integral I actually have two factors. In the first term I have r divided by r0 cube, because r squared and r cube cancel. In the second term I have a minus sign here, r1 to r0, r1 cube divided by r0 cube minus r1 cube, both cases. That's also a constant. I could have taken that outside the integral, divided by 1 over r squared dr. So let's do that. Maybe take that factor outside the integral. And the first integral just tells me r0 squared minus r1 squared divided by 2. How about the second term? The second term, I have r1 cube here, minus 1 over r squared gives me minus 1 over r integral at r0 and r1, right? So what's the result? Q over 4 pi epsilon 0 r0 cube minus r1 cube. Here I have r0 square over 2 minus 1 square over 2 minus the first thing becomes plus R1 cube over R0, and the second expression is minus, actually this is going to be minus and this is going to be plus, right? 1 over R1 square. Let me be sure about those. No, that's going to be plus and this is going to be minus. Yes. So all in all, I can collect these. My end result is 4 pi over 0 R0 cube R0 square over 2 minus 3 over 2 R1 square plus R1 cube over R0. I can leave the result like this, but just the aside about the signs here, which point will be at a higher potential, R1 or R0? Well, to go from R1 to R0, I actually moving with the electric field, which means the potential must be decreasing with increasing radius, so VR1 must be larger than VR0. And here, just to check, if you want, you can put R1 to 0 so that this becomes a full filled sphere. You will see that that gives me a positive result, and the correct result for the potential at R0. So overall, I think we found the correct result, and that completes the solution of the question.